Python 3.10, due out in October 2021, introduces the new match statement, which reimagines value comparisons and could significantly simplify your code, and might even change how you design data models, algorithms, and class hierarchies. I'm Andrew Kubera, and you're about to learn some of the syntax and semantics of the new Python match statement. Before we begin, I should say that the full specification and rationale can be found in PEP 634 and 635. There's even a tutorial on 636. Consult these for more information. Let's start with a simple contrived example function with a match statement comparing the argument x against three literal patterns. This is similar to a switch statement in C, Java, and related languages. X is known as the subject of the match statement, and the numbers 10, 100, and 1000 are the patterns. This is an important point, so I'm going to repeat this throughout the talk. These are not literal expressions, these are literal patterns. Adding a, say, times 1 here would be an expression equal to 10, but we see here it raises a syntax error because it's not an expression and does not get evaluated as one. When we run the function with different values, we see it behaves much like a standard if-elif statement, kind of like this one. Trying a number that doesn't match is ignored by the match statement, as you'd expect. Note that if we use the floating point number 10.0, it is found equal to the integer number 10 and will match because 10.0 equals 10. But if we use the string form of 10, that does not equal because this is all standard Python equality rules. Let's say we wish to also include the string form of the numbers in our match. We can combine two patterns using the OR pipe symbol like this. If this was a normal expression, this would raise a type error because a string does not support bitwise OR operator, but this is not an expression. This is a pattern which is now interpreted as does x match the number 10 or the string 10. This is what PEP 635 calls the OR pattern. Let's build upon this trivial example to examine a few more patterns. Capture patterns bind values from the subject into new local variables. Right now we're ignoring all other values not 10, 100, or 1000, so we'll add a capture pattern at the end which behaves like an else in an if-else statement, matching every other possible subject. Now when we pass in some random number, string, or any other object, it'll print this out. Oh, I forgot to add a case for the number 1. Let's add that here, and oh no, there's a syntax error. Python is clever enough to make sure that the catch-all pattern must be the last of the cases, because it always matches every subject, and any succeeding cases cannot be reached, which must be unintentional. It should be noted that the underscore variable is special in capture patterns, and will match but will not be accessible as a local variable in the block. This is strange as underscore is a valid variable name, but this is special behavior for patterns, and you shouldn't use underscores as working variables anyway. This is what the documentation calls the wildcard pattern. Now things start to get interesting with sequence patterns. Sequence patterns behave the same as typical iterable unpacking. There is no difference between square brackets and parens, and you can omit them altogether if you have commas. These are not literal patterns for lists and tuples, but rather patterns that unpack sequences and check for matches. In this example, we check for an empty sequence, a sequence containing only the value 1. Every other sequence containing one element that's not 1, because that would have been caught by the previous, and the wildcard to indicate nothing matched. We see tuples and list work. Also, ranges support sequence. Maybe surprisingly, strings do not match sequences, though you can unpack them. Iterators also do not match sequences, nor do sets and dicts. If you're familiar with iterable unpacking in Python, then you already know the sequence pattern's next trick. You can capture a variable number of elements in the sequence by placing an asterisk before a variable name, which I'll remind you again is a capture pattern. In this pattern, we are matching a sequence starting with 1 and storing the remaining elements in the variable tail. In this case, if we pass in 1, 2, 3, a new list with the value 2 and 3 will be stored as tail. Next comes the mapping pattern, where we match key value objects like dictionaries. First of all, it looks like a dictionary literal, but remember it's a pattern, not a literal. These patterns check if all the keys are present in the subject and that each associated value matches the corresponding pattern. Here, value is not a string, but a literal pattern that matches the string value. Let's make a dictionary that will be matched by this pattern. Again, the dictionary subject does not need to be equal to the pattern for this to match. It just needs to have the correct values. I'm going to create a fake scenario where we want to print user information passed in as a dictionary. Maybe it's loaded from a JSON file, but formatted using the match statement. The first thing we're going to do is check if the user is an admin by seeing if the admin value matches true. If so, we're just going to return because we don't want to leak any of the admin's data, just the user's, right? Then we can use two capture patterns to get the ID and name of the user and print that to the console. If the user doesn't have a name, we can match that by just doing another check for user ID. If that matches, we know the user doesn't have a name, and we can print a warning. All other values either don't have a user ID or are not mappings, so we can raise an error saying that the value is bad. Remember, all the other information in the dictionary is irrelevant, as the mapping patterns only care about the keys they're matching. Okay, we're getting near the end. Let's take a look at class patterns, where we find even more power. Class patterns automatically check if an object is an instance of a class and also checks if the object's attributes match all given subpatterns. Again, I want to stress that this is not creating an object and checking equality, but making a pattern and seeing if the object matches. This is another pointless example where we're matching the subject against types list, set, and int. There's no attribute check here, so this is not much more than calling isInstance. You can see here that 901 is correctly identified as an int, and 901.0 is correctly identified as not an int. Let's say we are writing a user interface, and the framework gives us a stream of events that we must process, so let's write a function called handleEvent to do this. We can use a match statement with class patterns to dispatch actions based on both the type and attributes of the event we're given. The first of these made-up events will be a keyboard event, where the attribute kind is key down. We can use a capture pattern to extract which key was actually pressed. Then we can do a similar action for the key up event. Similarly, we can check another subclass of event, the mouse event, using a sequence pattern to grab the x and y coordinate of the new mouse position. Another mouse event can be matched to detect a button press. I'd like to point out that we could be looking at two subclasses of mouse event, maybe mouse move and mouse press classes, or maybe it's something more complicated. By using attribute checking of a base class, and to be clear, a base class that does not have those attributes, we can potentially simplify some rather hairy logic. Just be sure you're unit testing properly. I'm not saying that this is better than other solutions, just that it's now available as a rather elegant tool. Let's stop with all these silly examples and do something more useful, like implement Fizzbuzz with the match statement. Here, I'm going to take the mod of the argument against both 3 and 5 and match both together. This tuple is the subject of the match. If remainders are both 0, the number is divisible by 15 and we return Fizzbuzz. If it's divisible by 3, we return Fizz, and if divisible by 5, we return Buzz. For everything else, there's MasterCard. No wait, that's not right. We return the number as a string. And we can run it against some integers, and you can see that it works. We are rapidly running out of time, but I wanted to mention placing local variables in patterns. You cannot by default, as names are interpreted as capture patterns, but you can put them in a class and access them as attributes to get the value within the pattern. Watch this later at half speed to see what's going on. Oh, and if you were wondering if you could match a regular expression match named match, you can. The name match is still allowed. And with that, I'm about out of time. I hope you learned something, and I apologize for rushing, but there's a lot to be excited about with Python 3.10 and the match statement.
and a lot I wasn't able to get to due to the time limit, so I hope you will have a look at the PEPs and continue on learning about it. Have a great rest of PyOhio.